Okay, in this video we'll have a look at line integrals in vector fields. And let's just begin by making some sense of all this notation that's starting to collect as we discuss line integrals in vector fields. So when we have a continuous vector field, f, that's given by some vector that would have this kind of form, and what you expect when you read this is that m, as I've indicated here, it's a two-dimensional vector. It could be three-dimensional. I'm just going to run through in my examples, I think initially here with 2 dimensions. So let's say f is a vector field in 2-dimensional space, and that means I can interpret that m as a function of x and y, and n also as a function of possibly both x and y. I mean, they are potentially x and y in the first component and potentially x and y in the second component. I mean, they could each of them have only one variable or even no variable. They could be both constant components. But the idea of the vector field is some vector function that has an x and a y component when we're in 2D, that at every point in that two-dimensional plane you have a different vector depending on what x, y you choose and what the m and n value turns out to be at that x, y point. So it's this field of vectors that are determined by these functions m and n, right? And then we'll also enter into this analysis, this smooth curve that doesn't have any corners or cusps, so that we have continuous derivatives. So a smooth curve that's given by some also a vector valued function that has a component that I'll call x and y, and these could be, these are typically, the x would be some function of parameter t, the y is some function of parameter t, so that we might think about as the increments of t, the increments of the parameter continue, we'll trace out some curve. In this case, this is a position vector, right? The r is the position vector for, I mean, it would be same in 3D. R is a position vector for the curve, and it's traced out. It's generally something that would be given parametrically. So it's traced out by some parameter t. Okay, this first line that I've written here shows sort of 3 different ways to look at and interpret what a line integral could represent. So this is some curve c that's given by, I could have said right here, so the curve c is given by the position vector r. So if we integrate the function, the vector field f, on the line integral over this line c with respect to r, what the heck does that mean? What the heck is that dot doing there? That's kind of new. So I would maybe first start to try to interpret this by saying that we are adding up the components of this vector f that are parallel to the position, that are tangent to the curve, sort of parallel to the path. That is actually parallel to the velocity. And if we imagine a particle moving on along the path, we're adding up the components of the force F that are parallel to that velocity of that position vector. I mean, this is interpreted as I'm describing it as work done by the force over this curve C with respect to that position. So this is one interpretation of a line integral, and one general form. And trying to make sense of that, obviously when we're just given a curve C here, we don't know exactly what the bounds are, and we're not going to find necessarily R here. It's not like we're going to integrate with respect to R actually. So we need to find other forms in order to evaluate this sort of general representation. But the general representation gives us some insight into what it really represents, and I'll try to talk some more about that as I go along. In fact, this part, the second expression here, illustrates a little bit more what I was actually just trying to say as I described in the first expression. The dot product of the vector field with this vector t, this is the unit tangent vector. So when you take a dot product of the force with the unit tangent, this unit tangent is the unit tangent to the position, to the curve of the position. So we're, again, I'll say what I was just saying before, that we are actually adding up the components of f that are parallel, you could say, to t, which is the unit tangent vector. So the part of the force that is parallel to the path and integrating with respect to the length of the curve over which, the length of the curve c. That's what that says. But what the hell do you actually do that? So one way to sort of make some sense of how you actually compute something like this is to go back to look at what is this big T. I mean by this the unit tangent vector. So this is definitely a vector, and you could put the arrow on top of that, which means you could put an arrow on top of that, which means you could go back and put arrows on top of the F and the R and then a bunch of arrows, and it just suddenly becomes kind of messy and cluttered and complicated. So that's part of why those arrows aren't there, is just because it's cluttered and it's understood in the context. So if this was being typeset on a computer, we might choose boldface symbols for those vectors, and it's not quite as cluttered to have all those arrows sitting there. So it's just not. It makes it messy to write the arrows. So we just have to know from the context that this actually is a vector valued function, this unit tangent vector, and unit tangent vector is always parallel to the velocity, but it's only unit length. It is the rate of change of the position with respect to the arc length. That's what the S represents. But I often don't compute the unit tangent vector by actually using an arc length parameter. Often, in order to compute the unit tangent vector, I'll just take the derivative of the position vector and divide by its magnitude. So that's really looks the way that I can make sense of this in a physical way, is to think about this r prime as being velocity, and then this denominator as being the speed. So if I took the velocity vector, divide by the speed, then I get this unit tangent that is basically the same direction as the velocity vector. It tells you what direction the particle is moving along the path, but it is always a unit length. The t vector is always a unit vector. So velocity divided by speed is another interpretation for this unit tangent. And actually, to make the jump from this expression to the one that I have at the end here, I'm going to go back to think about one way that you can interpret that speed, magnitude of the velocity, is as a linear speed. So it is the rate at which you are covering the arc length of the curve with respect to the parameter t. Basically, the t could be any arbitrary parameter. So if you measure how much length you travel on the curve with respect to that parameter, that's the speed. So it's down here that I sort of worked out the equality that I have here, the second equality, to go from f dot t integrated with respect to the arc length. I'm going to replace the unit tangent vector with this r prime over magnitude r prime, and I'm going to replace the ds with the speed times the differential in t. Just multiply the differential in t over on this side, and you have an expression for the differential in s. This is the differential in s. So replacing the differential in s with the magnitude of r prime times the differential in t, I realize, okay, these guys are equal and can cancel, and so I have another expression for the line integral now with respect to any arbitrary parameter. It doesn't have to be the arc length parameter, and so I'm integrating with respect to the parameter in which the position vector r is given. So we can do the line integral finally if we have a parameterization for the curve. What we'll actually do is just take whatever happens to be the This is some independent, given separate from the position vector, right? There's a path given by r, and there's some other, like a force acting on a particle following the path. So what we're integrating here is the component of that force that is parallel to the velocity. This is the velocity, and integrated over the curve that's traced out by that position vector r with respect to the parameter that specifies that path. And then I'll just add in that what that actually equals to is actually something that you can call work. You can say that this is the mechanical work from the definition in physics for work. It is the work done by the force F on a particle that follows the path r. I mean, we could interpret it as work. That's one of the applications that I will use this for to illustrate what it's for. Although it's not the only application, and it's not the only interpretation, but it's one that works well as you begin to learn this. So imagine, maybe you've seen from physics that work is force times distance. But now what if the distance that you travel is along a curve through 2D space or 3D space? So that's what we're getting here with this Calc 3 notation is the total work done by the force F on a particle that follows the path r that's parameterized with the parameter t. There's a lot of work just to say it. Yeah, it's not trivial. Let's see. Oh, and there's another way in which these things are actually not usually, but anyway, they're often written in one other way. And so let's say if you had this integral over some curve C of some force vector F dot some derivative of the position for the path through that vector field, and we're integrating with respect to the parameter that specified that path. Well, I was talking about how this F at the very beginning is made of these components, m and n. So let's put that in and see another way in which this thing can show up. So m could be some function of x and y, and this could be some function of x and y. So it's simple enough, and I could put extra parentheses. It gets really cluttered, right, to do that. So realize that m is not a constant. It's a formula with x's and y's, and this is a formula with x's and y's, and it could be anything. And then this guy, now this is the derivative of the position vector for the particle as it moves through the vector field, right? So that was given, r was given with components x and y, and so this is the derivative with respect to t. So here you can put dx dt, dy dt. So this is f, some vector field in the two-dimensional space. This is r prime, and it is the velocity of a particle that is moving through that vector field. Well, now I can do this dot product if I so choose, and I do. So the dot product was first component times first component, second component times second component. And so it looks like that, and then, well, it's simple and profound and complicated, and simple and complicated at the same time. I mean, I'm going to distribute the dt, or let's say if we integrated all this with respect to t, it's equivalent to canceling the dt's. So that's where that other form comes from. Usually what I think we're going to end up actually doing for most of the calculations will be changing the differential in x into a differential in t, changing this into some differential in t, and then putting all the differential in t's at the end. It is possible that you could integrate with respect to x, plus and integrate with respect to y over the interval and then add those two results together and get the answer that way. But I don't think that's normally what you're going to do separate. I think the examples that we're going to see most frequently, it's going to be replace the dx and replace the dy with a differential in t and integrate over some parameter from some t value a to some t value b. So certainly that's what I'm going to do in the next example that I want to look at. All right, so let's start off an example. This line integral here, given in this differential form, integral over the line curve. You have to switch back and forth because we say line integrals when they aren't necessarily straight lines on which we're integrating. That C could be a curve, but it's, I don't know, we pick up the phrase line integral when we could be saying curve integral. So we're doing the curve integral y squared dx plus x dy, where the curve C is actually a line segment that goes from the point -5, -3 to the point 0, 2. We'll do it first on that particular curve C, and then I'm going to use a completely different curve that's given by an actual curve that's a parabolic curve. It's a horizontal parabola x equal 4 minus y squared. But those 2 points that we just did in part A are points on this parabola, and so I'm going to use that particular curve to do the line integral on that particular path through the two-dimensional space for this particular, let's say, integrand. You know, when I'm looking at it, I do know what that capital F vector field would be, but I don't need to necessarily think of it or interpret it as a force or anything like that in this particular example. We'll just proceed to compute the line integral in the following way. So what we need to do is to parameterize the curve so that we can integrate with respect to t, because that's a nice way to do it. Is I need to actually get the path into, I need to get bounds, right? So, you know, I don't want to think about necessarily what the x bounds might be and what the y bounds might be and separate them. A nice direct way to approach it is to parameterize the curve and do substitution. So starting off with part A, so I have the point -5, -3. There is direction orientation indicated here by the word 2, so it's from this point to the point 0, 2. So let's say that's there. And so how can I create a position vector that traces out that path? Well, we've done this before. Let's say if I want the orientation to be from this point to this point, then what I could do is think of some, let's say, direction vector. I'll call it V. So that direction vector is basically the vector that is parallel to this line. And I'm creating the equation of this line in two-dimensional space in a parametric form. That's it. That's exactly it. And so what direction vector can I use here? It actually has to go, let's say, actually I can say it has to go over 5 spaces and up 5 spaces. So 5, 5 is the direction vector because that's basically the run first and the rise second. So that really captures the slope right there, right? It's the direction vector for that line. Over 5, up 5. So if I want to trace out a position, what I could do is maybe think of like some initial point R0 as actually, initial position vector that points to that initial point. So all I have to do is turn that point into a vector that is an initial position, and I want a terminal position, the 0, 2, as a vector, so that it's sort of like a terminal position for my position vector, 0, 2. So I could call it, RT or whatever. I use 1 because what I'm about to do is parameterize this just as t goes from 0 to 1. You could really pick any increment in the t that you want to trace this out, but that's completely arbitrary, so we can just make it go from t equals 0 to t equal 1. I'm going to have r. R would be like here. R is like this red vector that will actually, I needed to stay put there, and then I want to move this guy. So R is going to go like that and trace out the curve C. So the way to build a parameterization of that line, knowing an initial point and a terminal point, is you could just say start at the initial point, and then add to that some fraction of the direction vector. I'm really just using r equals r0 plus vt. That's the line in parametric form. It really is just like a line in 2 dimensions. You've got sort of an intercept here and a slope there. Intercept in the sort of t dimension. When you plug in 0, you get the initial position on the line. So C is traced out by this position vector. I now have parameterization x for the x and y positions. The parameterization is -5 plus 5t, and the y equals -3 plus 5t. And this is all assuming that t is between 0 and 1, so that we trace out just the segment, not the entire line. So when you plug in 0, you get that initial point, and when you plug in 1, you get the terminal point. Now to finish off this particular line integral, we can actually change it to an integration with respect to the parameterization for the position vector for the curve. So we'll start at t equals 0 and go to t equal 1, and the y values in this integral will be given by, the integrand is given by the y values as you're following that path. So the y will be just whatever the y is on that path. So it'll be -3 plus 5t in terms of the parameter. That's the y, so it has to be squared. So I have y squared times the differential in x. So I can write the differential in x as, well, I should say I can get the differential in x by using the differential in x with respect to t. That is, the derivative of x with respect to t is just 5. So that tells me that differential in x can be written as 5 times the differential in t. So then we'll write in equivalent to the differential in x is the quantity 5 times differential in t, and then plus now the x given by the quantity -5 plus 5t, meaning that as t increments from 0 to 1, we know what the x value would be for any point on this curve. And that x would be given by the parameterization of the curve, and then the actual integrand uses the x value here times the differential in y. So how do we get the differential in y? Well, just like I did before, I'll do the derivative of y with respect to t. The derivative of y with respect to t, well, that's actually also 5. So the differential in y with respect to t is 5 dt. So there's another 5 dt. Okay, so now this is all integrated with respect to t. So essentially, we could say we factor the differential in t out. We're doing both of these integrals with respect to t, but on the same interval. So we'll just do integration on that interval all with respect to t. So 0 to 1. This will be 9. I'm going to FOIL this out. That'll be -30 t plus 25t squared. Actually, it's still times the 5. And then this will be plus, that's 5, it's a negative 25 plus 25t. And then I'm just writing all the differential in t, both differential in t's at the end. So distributing the 5. Let's collect like terms. This was 25t. So they don't combine, but I do have 45, take away 25.
I'll collect
so
like
that's
terms
just
and find an
antiderivative, and then plug in the bounds. So there it is. That particular line integral is equal to negative 5 over 6. But what the heck does that mean? So to try to make some kind of sense out of that negative 5 over 6, it doesn't really have to make any particular sense at all, but to sort of try to find something there, to say that that's equal to negative 5 over 6 is like you could imagine that there was some function f that produced a vector field, and in this particular case that vector field would be associated with this function where you have in the first component a y squared and in the second component an x. And there's an m and an n in my sort of notation for vector fields. So looking at this line integral back in this vector form, I'm really, in calculating an answer of negative 5 over 6, I could think of it as almost like, what is the work that this force F does on a particle that moves along the path given by C, which was actually a path that I didn't actually draw here, but the path was from this point up to the point 0, 2. So as the point moves along this path, from t equals 0 to t equals 1, it traces out that path. Doesn't really matter how long it takes, how I do the parameterization. I would still get the negative 5 over 6 for that path for this vector, the work done by this vector field, or this vector force field on that particle as it moves along that path. It's a negative value, which means it's sort of moving against the force. The force is kind of losing if it's a negative. It's moving in a direction opposite the force. So, yeah, it doesn't really have any much. I don't associate any natural force field with this particular function f. We'll do some other ones where I'll use the force due to gravity as a vector field, and then I can really interpret absolutely a meaning for the line integral. Here we're just practicing the operations and the notation, and I have one more to do, so let's go on to part B and compute the same line integral but with a different path. So for part B, so there's conditions under which the answer would be the same, and it's whether that vector field was conservative. And I haven't really gotten into the details of what that actually even means yet, but you'll see that actually this is going to come out to a different answer, and so this vector field isn't a conservative vector field because we're going to get a different answer, even though we're following, well, obviously we're following a different path. We're starting and ending in the same points. Let's take a look at the path this time. It's a different path, same starting point, same ending point. This is a parabola that has a x-intercept at 4. If you make y 0, you get 4. And let's see, if I make the x 0, then I'll get plus or minus 2. So now C has been changed. So I'll still call it C, but we could have called C1 and C2. So we need to find this line integral. So best thing in the circumstances with the information as it's given would be find a parameterization for the curve, and then if that parameterization is in terms of t, we can replace the differentials dx dy by a differential in t. So since I have the a curve, if the x position depends on the y value, what I can actually do is make the y value the actual parameter and just do 4 minus y squared and then y, and then let y go from -3 to 2. So that parameterizes the curve with the parameter y. So actually, yeah, what's going to happen here is I have a parameterization that says x is a function of y, and the y is a function of y. So I'm not going to parameterize in terms of t. I'm going to parameterize in terms of y. And let's see. So then x is a function of y. 4 minus y squared, and y as a function of y, let's just say that the y is the y. So if I choose to parameterize the curve in terms of y, then I can go from y equal -3 to y equal 2, and the y value is just y, and now I need the derivative of x with respect to y, because I need to relate the differentials. So differential in x is actually -2 times y, differential in y. So replacing the differential in x with the differential in y, it would have to carry along a -2y times differential in y, plus whatever the x value is, which is actually parameterized in terms of y, and the differential in y, it's sort of like the derivative of y with respect to y is 1, so the differential in y is just the differential in y. So here I have -2y cubed. So this is a good one where you see that it didn't actually have to be always parameterized in t, as I was just even saying a few minutes ago. It isn't always, so here's how it might not be. Depending if you have a curve where you have, if you can isolate one of the variables for the curve, then that suggests a way in which you could parameterize the curve. The dy and finding an antiderivative. I'm going to plug in the bounds, and it's all calc 1 here. So as I plug in the bounds and go carefully with all those pluses and minuses and simplify, get down to 245 over 6, a positive value. So now the line integral on a different path comes out to a different answer. So it's sort of like the force is kind of winning. I know you just cannot resist the Star Wars ideas. You know, I have this, I could imagine a vector field, a vector force field F, and the work that it does on a particle as it moves along this path. And along this path, that force, it does positive work. So it's sort of like the path was such that the object moves in the sort of in a total sum, more or less in the direction in which the force is applied, or it's moving more often in the direction in which the force is applied than against the direction in which the force is applied. And so we end up with a positive in the end. I mean, it was absolutely forced for me to try to conceive of any way in which to think of this as work. I mean, it doesn't really make any sense. I mean, it's completely arbitrary. If that force field F was, I mean, if that vector field was a force, this would be the work done by that force moving on this path. And it turned out to be a different answer, which indicates something about the nature of that vector field that this particle is moving in, and that's something I'm going to get to in another video. It means that the vector field is not a conservative vector field, but that would be too much to go to also in this same video. So I'll just say that in absolutely general terms, they aren't necessarily, even though the starting and ending point were the same, these two different paths lead to different values for the line integral in general. There's something specific about the vector field that if it had the condition that it was a conservative vector field, then these answers would have turned out to be the same. They didn't have to be, and they aren't in this case. And also I want to say something like the fact that even though I kept working with the interpretation of these line integrals as being work, that isn't the only interpretation. I can think of line integrals as related to areas when the line integral is over a closed curve. So I have some other ways to interpret the line integral besides just work done, but that's like the first place that I want to start in trying to give it some meaning, is to speak of the work done by the vector field F on a particle that follows that path given by the position vector r. In this case, it was positive work. All right. Okay, so I realized that I could get this into Mathematica, this vector field with these two different paths, and it really wasn't that hard. So you can see here how I entered that in to generate this picture. So this is a picture of the vector field that we were analyzing with the two paths that we computed line integrals on. So now we can make some sense as to why one of the line integrals was positive and negative in a sort of graphical way. So let's give different names to each of these paths. We'll call this path C1. We began there and traveled in this direction, so we could also add on an orientation. And then we'll call this path C2. And the orientation that came from the parameterization was that the particle moves along the path in this direction. Now, we did this one first. We began at the point -5, -3, and we travel along this path up to the point 0, 2. And what I could see here is that why did the answer come out negative? It's because along this path, most of these vectors that come from this vector field are pointing in direction opposite to which I'm traveling. Or, the components of each of these vectors. Like I'll pick this one right here. The component that is parallel to the path is going to be in a direction that is opposite to the path, opposite to the direction in which we're traveling. So overall, there is negative work done by this force that's illustrated by all these little vectors in this vector field. That force is doing negative work on this particle as it travels along this path. Taking the other path, positive work was done by this force shown in the vector field, and that's because all of the components of these little vectors are, the components that are parallel to my path are in the direction of the path. So the components are smaller maybe here. If you look at the tangent vector would be somebody like that. That's a tangent vector to the path. And then the component of the vector field, the force given by the vector field, the component that is parallel to that is actually in the direction of that vector, not the opposite direction. So we're getting a positive amount of work done in this little increment of distance, and then that continues, particularly along this part of the path. We're getting components that are here exactly parallel, all of the forces in the direction of the particle as it moves. And then perhaps here we begin to lose the total amount. There's negative amount of work done here, but overall the net amount of work done is positive along this path. So it's kind of fun to think of that as sort of like along path C1, this force is kind of losing. The resistance is winning along path 1, and because it's moving against the force. Where the particle is moving against the force, where along C2, along that path, this particular force is kind of winning. It's moving in the direction in which the force wants it to go. You know? So it's joined the force. It's more. There's less. The force is providing less resistance. I guess the particle is one with the force, or more not precisely one, it's not exactly parallel to the force, but it's moving in a way in which the force is the force is getting positive work done as we follow along this path C2. The force kind of overall wins if it follows this path. Okay, so I think I'll stop this example. I'll do some more similar things in another video, but that's probably enough for this one, so we'll stop there. I hope it was interesting and helpful.